Well, thank you, Carlo, for the opportunity to present this research, and thanks to all of you for sticking with us to the end. So this is the last session of the day. Thanks for staying with us. Today, I will be talking to you about a machine learning approach for identifying private wells susceptible to chemical contamination. And this is joint work with researchers from Harvard University, and I also like to thank the data provider as well as the funding agency for this work. So over the past 50 years, the US has made impressive improvement in air quality. You see that air quality drops by more than 80%, while the economy remains strong. However, for drinking water, the picture is much less happy. Easy Google search on the internet, you will see a lot of drinking water crises happening in multiple communities in the country. So why is that? I would argue that it has something to do with how drinking water quality is traditionally monitored, because you know what gets measured gets improved at the end of the day. And traditionally, drinking water quality is measured through grab sampling. So you need someone to go into the field, take a sample, bring it back to the lab, and analyze it. Definitely this process sounds tedious and expensive. You're going to have low coverage problem. The results are going to be delayed. More than that, for private well users, because their drinking water source lives on the individual property, these water quality is not subject to Safe Drinking Water Act, which is the governing law for drinking water quality in the US. And we're talking about 43 million people here. That's 15% of the US population. If you take a look at the map on to the right, a lot of these communities are away from city centers and in the more remote areas. So studying them also has implications from the environmental justice perspective. A study from the United States Geologic Survey in 2009 found that more than 1 in 5 of them were contaminated at a level of health concern. So that brings me to the topic of today's talk, which is, can we use machine learning models to predict where private well drinking water contamination is more likely to happen? So how do we do that? On a high level, you need to integrate multiple different data sources. And here you have layers of geology and information about industry emissions, as well as hydrology. You can extract the values around the location of private well and bring all those predictors into your favorite machine learning models, whether it is tree-based or neural nets, and here I'm going to use tree-based models, and see if you can replicate basically the spatial distribution of contamination in a state. So here I'm going to talk to you about a case study we published last year in the state of New Hampshire, and it's going to be around a group of chemicals called PFAS. You can find them on Teflon pans or other surfactant coatings. They're also known as forever chemicals because it takes almost forever for them to break down in the environment. Let's start with the data sources. So as with most of the supervised machine learning models, you need some well-labeled training data. So for our study, we get data from New Hampshire Department of Environmental Services. They have measured PFAS concentrations in more than 2,000 private wells. Unfortunately, the data is quite heavily left censored, which means that you have a detection limit, and anything that's below detection limit, you can't really have a reliable number associated with it. So we have to dichotomize our outcome to be binary, basically detect versus non-detect. In terms of predictors, we're mostly talking about 2 big classes of predictors. First, we have point sources. So these are potential emission sources for PFAS contamination. And we're identifying those industry locations using the NAICS code or the North America Industry Classification System code. We calculated an impact score, which is basically a measure to quantify the impact from that industry location to the drinking water well. And this score takes into consideration not only the distance between the source and the well, as well as the direction, because like groundwater has a certain flow direction, and it won't really make sense for us to imagine a downstream industry source impacting an upstream well. So we need to take into consideration the direction as well. On the other hand, you have some environmental predictors, and they're all listed on the slides. I'll just mention that for generalizability, we prioritize nationally available predictors for this work. And so how are the models performing? We're using the ROC curve to evaluate the model performance. And if you have a perfect classifier, they should go through the top left corner of the graph. And here you can see that we compared random forest with more traditional like logistic regression. And we found that random forest outperform the logistic regression models in almost all the cases. Moreover, we can also use something called variable importance plot to look at what are the predictors that contribute to the predictive power of the model. So here I'm like listing the different type of PFAS from left to right. You range from shorter carbon chain to longer carbon chain. And then on the different rows, you have different types of predictors. Some of them are around industry point sources. Some of them are around geology or hydrology or soil properties. And you can look at individual groups and look at the predictive score, collaborate with the subject matter expert to assess whether the model makes sense. So here we can see that some of the top predictors are impacts from plastics and rubber industry. We can see that precipitation is quite important, and so is air deposition. And soil properties are more important for some of the longer chain compounds. So far, we haven't talked anything about spatial, right? So like if this is actually quite common in random forest models, a lot of times even the data itself is spatial. They were analyzed in an aspatial fashion. So we want to revisit our model by taking into consideration some of that aspect as well. So if you recall from the map you see a few slides ago, our data points are not randomly, evenly distributed all across the state of New Hampshire. They're quite clustered in the southern part of the state. So we are potentially going to be worried about autocorrelation in the residual, and why that matters, because a lot of statistical techniques really rely on the IID assumption, and that's independent identical distribution assumption to work properly. So we evaluated the autocorrelation in the model residuals, and we can see on this graph that indeed the residuals are clustered up until about 6.3 kilometers. So how do we address this spatial autocorrelation problem in our data? And I would say this is still a quite active area of research, and there are multiple ways of addressing it. Here I'm trying to implement something called spatial random forest, which is just one of many ways to address this problem. And the way it works is by incorporating a lot of spatial predictors. And you can think of spatial predictors as these pairwise neighborhood variables that indicate how close each data point is to all the other data points in your data set. On the right-hand side graph, here is the variable importance plot from the spatial model, and compare that to a non-spatial model. You can see that some of the spatial predictors actually achieve quite a high variable importance score, and they're even more important than some of the aspatial predictors. So the bottom line, how does that impact the predictive power of the model? If you look at the table to the bottom left corner, they are about the same with the non-spatial model, to be frank, but you do see that the spread of AUROC change a little bit when we move from non-spatial to spatial. If you are paying really close attention, you will notice that these AUROC scores values are also lower than what I showed you a few slides ago. And why is that? And this is because we switched from a random cross-validation to a spatial cross-validation. So random cross-validation, I'm sure many of you are very familiar about the concept in your work. You basically create a random split between the training data set and the test data set. But because our data is spatial in nature, you inevitably end up with a situation where your training sets and your testing set are quite close to each other. And everybody in this room knows the Topler-First law of geography, so some people are concerned that this may create leakage between your training set and your test set. An alternative way of evaluating your model performance is to do this spatial cross-validation. And this is to ensure that your training data set and your testing data set don't touch each other, like they don't mingle spatially. Personally, I would argue that one is not always better because when the spatial cross-validation may paint an overly pessimistic view of your model performance, especially if you don't intend on extrapolating your data from where you have training data points to the areas where you don't. Another methodological consideration when we train models to predict drinking water quality is to select the best or the most appropriate, I should say, model performance metric. Accuracy, for example, sometimes is not a great metric if you have highly unbalanced sample. And I won't have time to go into all the different potential performance metrics we can use, but I encourage you to check out this review article that's going to come out very soon on the current environmental health review. So I want to end this talk with a few thoughts on how we can move forward as a field toward building a national model for investigating these contamination in private wells. And as you can see in this animation, like this, is the animation playing? Sorry. Well, the animation is not playing. Is it playing now? Well, sorry about the glitch, but originally you should see an animation of different contamination sources all across the country, so there's urgent need of identifying like communities that are most susceptible to these kind of drinking water contamination. Hopefully this talk today gives you some idea of maybe how like machine learning techniques can be useful, but I would argue that we still have a long way to go and we need to make a lot of advancement in both the data front as well as the method front. On the data front, there should be better infrastructure for data sharing. So as the individual investigator, you can more easily share your data and help your colleagues to build better models. And on the method front, we need better techniques to address spatial autocorrelation in the data, as well as choosing the best model performance metrics. And that's all I have. I will end with the reference slide and take some questions if we have time. Thank you very much for your attention.